crisis in cosmology is one of the biggest problems facing astrophysics today. But now there's a research group that claims to have solved it using data from JWST. Now, if you've been following me for a while, you'll have heard me talk about the crisis in cosmology before, and so you'll know how incredibly huge of a deal this is. So to quickly recap, we have two main methods for calculating the current rate of expansion of the universe. One from our model of the entire universe, and one from observations of nearby galaxies. And as telescopes and analysis methods have improved over time, those two methods have started to give us very different numbers for the rate of expansion, what's known as the Hubble constant, to the point where they very strongly disagree with each other. This is known as the Hubble Tension, or the crisis in cosmology, if you want to be a bit more dramatic. But last weekend at a conference of the American Physical Society in Sacramento, California, a giant in this field, Becky Freedman, presented her research group's latest work using data from JWST, and now they're claiming a value of the Hubble constant that, within error, agrees with our best model of the universe. They're claiming now that there is no Hubble tension, that the crisis in cosmology has been solved. Now, of course I had to make a video on this, but everything I'm about to say comes with a very big disclaimer. No research papers have been released yet. This work is not peer-reviewed. All we have to go on is the 35-minute talk that Becky Freedman gave at this conference and the slides that go with it. That is not what I usually like to do on this channel. Just last week, I mentioned how I like to wait for papers to be peer-reviewed before I make videos on them. So I'm aware this is very hypocritical of me to be covering this, but I just didn't feel like I could ignore this. This feels like the proper cutting edge of research and discussion, especially since the results we've got from another research group using JWST data to investigate this have been suggesting JWST couldn't help us solve the Hubble tension at all. It made things worse, and I've covered that in a video just a few months ago on this channel. So there is so much to unpack here, but it comes with the caveat that everything I'm about to say could all change in the peer review process in the next couple of months. So in this video, we're going to chat first what the Hubble tension actually is in a lot more detail, and I'll pop chapter markers down here for all of you who've heard me say this before and you might want to skip that recap. Second, the possible explanations for the tension and what could solve it. 3, what Freedman and collaborators are claiming to have found using their data from JWST. 4, how this compares to previous work on the Hubble tension with JWST. And 5, what now? Is the crisis really over? Because it seems like what we've got is two research teams claiming two different things, both using data from JWST. Now, when you have two sides like that in science, the data and the observational evidence will eventually come down on one side or the other. But in politics or society, it tends to be a bit more complex than that. Which is why I like to use Ground News, the sponsor of today's video, to help me wade through the different opinions discussed in the media to see through the bias and the misleading narratives. Ground News is an app and website that compiles sources from all the world's media in one place. It's the brainchild of Harleen Kaur, an ex-NASA engineer who even worked on JWST. So of course they have great space news coverage, but where I think Ground News particularly shines is with their blind spot feed, which gives you a look into news stories that you might have missed depending on where you typically read your news. Take this story, for example, about how Austria is likely to be largely ice-free within 45 years as glaciers recede quickly. But you can see that people who only read exclusively right-leaning media sources might have missed this story, but thanks to Ground News' blind spot feed, it won't be lost in the mix. We can also see that 77% of the sources are rated highly factual, so we know that there aren't as many sensationalized headlines. I particularly love Ground News' comparison features. For example, right-leaning media sources put quotations around largely or ice-free, whereas left-leaning sources frame it around this is what experts have said. So this is why I'm proud to be partnering with Ground News. Again, they're an independent platform that works on a subscriber-based model so that they can be free of any advertising bias. So if you head to ground.news/Dr. Becky, you'll not only receive a 40% discount on their Vantage plan when you subscribe, but you'll also be helping to keep the media transparent. So thanks again to Ground News for sponsoring this video, and now let's get back to chatting about this huge news about the Hubble tension and chat in a bit more detail about what the problem actually is. So I've talked a lot on this channel about the Hubble tension or this crisis in cosmology before. I'll link a playlist of videos down below if you want a real deep dive on this. But essentially this all boils down to our measurement of the current rate of expansion of the universe, what's known as the Hubble constant, or H naught. The naught subscript here refers to a redshift of 0, i.e. the universe around us today, the rate of expansion now. Now, the rate of expansion does change with time, and we can also measure that, how H changes as a function of redshift Z. And that's something that the recently launched Euclid Space Telescope will focus on, and it's what the recent DESI collaboration have done. More on that in next week's Night Sky News video. But that's a separate thing to this current rate of expansion H naught, which is the measurement that's caused all of the issues. Now, one way to measure this current rate of expansion is to measure both the distance to nearby galaxies and the speed that they appear to be moving away from us because of the expansion of space. We then plot one against the other, and the slope of the line that you get is the current expansion rate H naught. When we do that, we get a value of around about 74 kilometers per second per megaparsec. Other way we can get at the current rate of expansion of the universe is to model the entire universe, starting with the earliest light from when the universe was just 380,000 years old, what's known as the cosmic microwave background, and then come up with a model that can evolve that into the universe that we see around us today. We then find the best fit model to, the observed universe in terms of like all the laws of physics that we know, what the universe is made of, and how much of everything there is. And then from that model, we can then determine lots of other different parameters and properties of the universe. One of those is how the expansion of the universe changes with time. But in particular, we can also get the current rate of expansion, H naught, which when we do that, we get a value of around about 67 kilometers per second per megaparsec. So this Hubble tension or crisis is because these two different methods are giving us two very different answers. There's a gap between them that's bigger than the uncertainty on our measurements, a gap which has only been widening over time as our uncertainties decrease, as our analysis techniques got better and our observations of the universe supposedly improved due to bigger and better telescopes. So how are we going to solve this? Because for them not to agree, either there's something wrong with our observations of nearby galaxies, perhaps how we're calculating their distances, something like that, or there's something wrong with our best model of the universe. Either we'd be missing some law, either we're missing some law of physics that we don't know about yet, or there's some component of the universe that we don't know about yet that we haven't included in our model. Like, this is the option that I think people get most excited about because it means we'd learn something new, there'd be brand new physics to explore and to try and understand. Here's a non-exhaustive list from a review paper last year of all the different hypotheses that have been raised to try and explain this with new physics. And it's why I got so excited when I first saw that this talk was happening at this APS conference last weekend. Because the title was New JWST Results. Is the current tension in H naught signaling new physics? I thought that that's what this research team had found, that they were going to present evidence with JWST that showed that we needed some new physics, which is why I got so excited and put out a short, an Instagram, and a TikTok. And from the poll I put out, it looks like all of you thought the same thing, but I guess we should have known better. Betteridge's law of headlines, right? So it's looking like it was something to do with option one. Now, option one really is where the majority of my colleagues' focus has been. You really do have to be meticulous with your science, exhausting all the possibilities that you could have got something wrong in terms of your observations before you start considering new physics. And the sort of thing that everyone was suspicious of, that they thought was going to be the issue, was our measurements of the distances to nearby galaxies, which we get with something known as the cosmic distance ladder. Before you can calculate the distances to nearby galaxies, you have to take a few steps up the ladder first. And the first step on the ladder is calculating the distances to nearby stars in our own Milky Way galaxy. One way of doing this is to use parallax. This is essentially using the fact that our perspective here on Earth changes as we orbit the sun. So we view stars from slightly different angles at different times of the year, which means that nearby stars seem to change their position slightly compared to more distant stars. From how much those nearby stars wobble around, we can work out how far away they are using simple trigonometry. Once you've got that, you can then take the next step up the ladder where you work out the distance to our nearest neighbouring galaxies. And to do that, we use something called standard candles. Types of stars that have like an absolute maximum brightness. And we know what that is because we've observed them in our own galaxy and we know how far away they are there, so that from how bright or faint they appear in more distant galaxies, we can then say, okay, well, from how bright they are there compared to how bright we know they should be, we can work out how far away they are and therefore how far away that galaxy is. There's a few different types of stars you can use to do this, the most famous being Cepheid variables. These are stars that pulse in proportion to that maximum brightness that they can reach. We know this from observing them in our own Milky Way galaxy, so if you can measure the time between pulses in Cepheids in neighbouring galaxies, you know what their maximum brightness should be. So from how bright they appear, you can then work out the distance to those nearby galaxies. There's other types of stars we do this as well, known as the tip of the red giant branch stars, TRGB, or the J region asymptotic giant branch stars, JAGB, which again have a known brightness in the Milky Way and a known distance, which again we can then compare them to in nearby galaxies. That means that those distance measurements all rely on our previous rung of the ladder, the distances of stars in the Milky Way itself. Now that's great for our neighbouring galaxies where you have a hope of resolving these individual types of stars, but for even more distant galaxies, you have to go another rung up the ladder. Because those individual normal stars are just too faint for us to pick out at those distances. But we can do it if a star gets incredibly bright in a supernova. Specifically what's known as a Type 1a supernova, when a dead star known as a white dwarf reaches the maximum mass it can support and then goes supernova, always with the same brightness because that maximum mass is always the same. So again, these are a standard candle, but because they're so bright, we can see them in galaxies much further away, and we can then use them to calculate the distances to those galaxies. It's using these supernova in these more distant galaxies that we use to measure that rate of expansion of the universe, and it's this measurement that's so at odds with the one that we get using our best model of the universe. But you've got to remember that the distances to those galaxies rely on those previous rungs of the cosmic distance ladder and all of the observations and calibrations that have been done to get to that stage. This is why this is thought to be the most likely explanation for the Hubble tension. The thought has always been that somewhere in this house of cards of the cosmic distance ladder, if just one thing is wrong, it could all come crashing down. And the hope has always been that the James Webb Space Telescope, JWST, would be the saviour of this research field, and that the data from it would help us figure out what's going on. One idea was that the middle rung of the cosmic distance ladder, using the stars in those neighbouring galaxies, was affected by something called crowding. So the Hubble Space Telescope couldn't actually separate the individual stars out very well. It didn't have a high enough resolution, so the individual star's light couldn't be isolated from the stars around it, so your measurement is then biased. But with JWST being a much larger telescope, it could resolve smaller things and therefore resolve the individual stars so much better, giving you a better calibration then for the next rung up the cosmic distance ladder to those galaxies with supernova, which is the data we use to calculate the current rate of expansion of the universe. Now, one research group led by Adam Rees has already looked at this with JWST data and made a video about it earlier this year, and they claim that this crowding problem is not responsible for the Hubble tension. The brightness you get for the Cepheid variables are very similar between JWST and the Hubble Space Telescope, so it doesn't change your results. Again, this is why I got so excited when I saw this title from the other research group led by Freedman that are also working on this with JWST. I thought they might have found something similar and be claiming that no, it's not the cosmic distance ladder that's responsible, But that's not what Freedman presented in her talk. So that brings me to what have they found and what are they claiming instead? So what they've done is focus on that middle rung of the cosmic distance ladder. With JWST, they observed these neighboring or nearby galaxies where you have a hope of resolving out these individual either Cepheid variable stars, TRGB stars, or JAGB stars that they can then use to calculate the distance to those galaxies. Now, crucially, the galaxies they've chosen also have supernova in them as well. So you can use them to calibrate the distances to all of those more distant galaxies that have supernova observed in them. And they've done this for the 3 different types of stars separately, so they can compare the 3 different methods of getting at the distances. Now, they've done all this with what's known as a blind analysis. So this is where you don't actually see any of the real numbers or any of the real values until the very end. So, you put together your analysis code that's going to take the images and work out the brightnesses of the stars and therefore work out the distances and use those distances to calibrate the more distant galaxies, and then finally spit out a value for the Hubble constant, the current rate of expansion of the universe. But you don't actually see the numbers as you do that, as you develop the analysis code and you double and triple check that everything is working as it should be at every single step along that chain. You don't see any of the real numbers because you either add random noise to your data or you use fake data. It's only when you're certain that everything is working as it should be that you finally put your real data in there. And that's a process known as unblinding, when you finally get to see the real value and the real answer. And what it means is that that analysis stage is then free of bias of what you expect the answer to be. The team apparently got to do the unblinding in mid-March. I reached out to them and they sent me these pictures of when they did the unblinding, and I just think it's incredible to see that sort of joy that science creates. Not only did they do this blind analysis, with the new JWST data, but they also completely reanalyzed all of the old archival Hubble Space Telescope data as well for all of the Cepheids and reanalyzed all the supernova data too. After doing all of this, the first thing they found is that for those 3 different types of stars they used, they all agree on the distances to those neighboring galaxies, which is great news. It means their data is consistent, and from there they could then recalibrate the distance to those, more distant galaxies with the supernova, and then recalculate the current expansion rate of the universe, and they get a value of 69.1 kilometers per second per megaparsec. A value that, within the uncertainties of about 1.3 kilometers per second per megaparsec, now agrees with the value from our best model of the universe using the Planck satellite data of the cosmic microwave background. It's not perfect, but there is some overlap, and statistics thankfully tells us not to worry. The fact that they're ever so slightly different could just be explained by random noise. It's nowhere near the level of difference that we had before, where statistics told us we really do have to worry here. And interestingly, I mentioned the DESI collaboration before that have just looked into that change in the rate of expansion over time, also managed to calculate a current rate of expansion using a completely different method entirely, something known as baryonic acoustic oscillations. And again, they found a very similar result at 68.52 kilometers per second per megaparsec. Again, more on that in this month's Night Sky News episode coming out next week. So it seems like we might finally be seeing some agreement between all these different methods of calculating the current rate of expansion of the universe. At least that's what Freedman and collaborators seem to be claiming at the moment with all of their careful blind analysis that they've done. But again, the big caveat that this could all change during the peer review process. But if we take it as this is going to stay like this, how does this then tie in with what we just saw earlier this year from another research group led by Rees and collaborators, who claim there's no difference between the JWST and Hubble results in terms of this crowding problem of the stars, and it can't explain away the Hubble tension? Honestly, I don't know at this stage. This isn't just cutting edge science. This is standing on the knife edge and just staring into the void of confusion. You know, this isn't something that's going to be explained in a minute of a YouTube video after I've puzzled over it for a few days, especially since I'm a black hole expert and not a cosmologist, right? This is going to take dedicated work by each of the collaborations, and I'm sure a lot of this is what's going to end up in the discussion sections of the research papers by Freedman and collaborators that will eventually come out after peer review. Perhaps it'll turn out that the crowding problem wasn't the issue and that there is no conflict between what the two research groups have found. Maybe it's something else in all of those endless steps of the blind analysis that Freedman and collaborators have done that, you know, has just come out in the wash, and that's what's reduced the Hubble tension. Perhaps there is actually a conflict here between what these two research groups have found, and maybe it's something to do with how they've analysed the data, and I do not want to wade into the middle of that. But just to highlight how difficult it's going to be for the research team to pinpoint which step in the analysis has actually resolved this Hubble tension, or whether there is a conflict or not. A difference of just 0.1 in the magnitude of these stars, i.e. the brightness of the standard candles you're measuring, leads to a 5% difference in the current expansion rate that you calculate. Or in other words, it can take you from a value of h0 of 73, i.e. there is a tension, to 69 kilometers per second per megaparsec, i.e. there isn't a tension. And so finally that leads me to what is next. Is the crisis actually solved? And to be honest, I think the only simple answer I can give here is we don't know yet. There's a lot more work to do, which is why I enjoyed one of the questions after Freedman had finished giving her talk, in the Q&A section, was from a theorist in the audience who was like, should I stop working on the Hubble tension then? Is it solved? Should I find something else to go and do? I think everybody wants to know the answer to this question. But I think, there's so much more work involved, not just for, the two different research teams using JWST to do this, but if it turns out there's something in the reanalysis of archival data that's led to this dissolving of the tension, then that might cause even more research groups to reanalyze a load of their old data and recalibrate it using JWST data, and that might have then a knock-on effect in other places. So if this result that's been claimed by Freedman collaborators holds through peer review, then this is not done and dusted. This is kind of like a heads up, everyone needs to redo all of their homework. So I'm very intrigued to see what happens next, what sort of discussions start popping up everywhere, especially as Freedman and collaborators continue to present this work on sort of the lecture and conference circuit this spring and summer. Freedman is talking again on this topic at the Royal Society in London in a few days' time at a meeting on going beyond the standard cosmology, which has been organised by some giants in the field, which if I wasn't already at a conference myself, I would definitely be going to, because I would love to be in that room to hear those discussions. I'm sure it's going to be a very productive meeting for them. When this work finally gets, published in a peer-reviewed journal, I will link it in the video description down below so that you can have a read of it yourself. I'll also make another video on this channel after reading all of the discussion section that, Freedman and collaborators put together and what they reckon might be responsible for this solving of the Hubble tension. And of course, I'm excited for the deluge of reaction research papers that are inevitably coming after a result like this is announced. So if you don't want to miss out on any of that, make sure you're subscribed, because I'll be covering it all right here on my YouTube channel. So to quickly recap every time. But last weekend, is it American Physics Society or American Physical Society? American Physical Society. It is the American Physical Society, which just makes me think of Olivia Newton-John, let's get physical. Without yet, so we haven't been able to include in our models. This is the one. So to solve this, then, right, my belly just gave it the most almighty grumble. We've got so much left to film, you can't grumble yet. It is an hour from lunchtime. Hubble tension, pushing on me. Oh, is it solved?